I have talked about how an optimization algorithm has an objective function, constraints and decision variables, and I have related all of these to the control viewpoint. And then I also talked about how we get a discrete model of the process, so that we can put together this model predictive control formulation. So, in this lecture I will quickly combine all of these together to show you how the optimization formulation is put together. And the beauty of this model predictive control formulation is that since we have an optimization formulation and not an analytical expression for the control law, any optimizer can be used to solve this problem. So, if you find a more efficient optimizer, you can simply use this formulation with that optimizer. So, the accent in terms of the model predictive control material is more on the concepts of formulation and how do we formulate this problem, rather than the solution, which is a standard optimization solution that you can use. In fact, this makes it very nice, because we can come up with various nuances and enhancements in the formulation. And while we are doing this, we do not have to really worry about how we are going to solve this, right. So, ultimately once you put all of this together, if you have an efficient optimizer that can solve the class of problems that you are interested in solving from a model predictive control viewpoint, you simply give it to the solver to solve it. So, in that sense, in some sense, the solution to the formulation is kind of decoupled to some extent from the formulation. That makes it easier for us to conceptualize this formulation better. So, I am going to recap some of the things that we have seen as part of this module. So, here is one picture which talks about how this model is used. So, for example, if you have an output at the kth time instant, then that is working with this envelope here, which basically says to predict yk, you need to know uk minus 1, uk minus 2 all the way up to uk minus gamma. Now, if you want to predict yk plus 1, what you do is you simply move this one step ahead, and also this envelope is moved one step ahead. So, if I want to predict yk plus 1, you look at this envelope here. So, I need to know uk minus 1, uk minus 2 all the way up to uk minus gamma plus 1, because we have slided this up one more. Similarly, if I want to look at yk plus 2, I look at this envelope here. So, I slide this one, slide this one. So, I need values for uk minus gamma plus 2 all the way up to uk plus 1 for me to be able to predict yk plus 2. So, this goes on. So, if I am at time k, I still can write these expressions for yk plus 1, yk plus 2 in terms of inputs that have already occurred, which are here, and input that I am going to make now, and future input. So, this is the key idea which we have talked about quite a bit. So, in other words, if I am interested in controlling my system and looking at how I am going to take my output values close to set points in the future, starting from yk plus 1, yk plus 2 and so on, basically what it says is I can write these as functions of the current manipulated variable value that I should keep, and future manipulated variable values I should keep. So, I can write these as a function of these manipulated variable values, which is what we have already talked about quite a bit in this series. So, now we have everything to put together this optimization formulation. As a recap, we are at the time t equal to k, and whatever control move that we are going to make at k, k plus 1, k plus 2 and so on, these will affect outputs in the future. So, they will start affecting the outputs at k plus 1 given k, k plus 2 given k. I already talked about given k, meaning we are at time t equal to k. Okay. So, these outputs up to yk plus p are going to be affected by the choices that I make, and the way I make my choices is that I am going to make a choice for uk plus 1, uk plus 2 all the way up to uk plus m minus 1. That means I am making m choices here. And then what I am saying is, after I make this choice here, then I am going to say I am not going to make any more choices, I am going to let the input be at the same value. Okay. So, when we formulate this, all we need to find is values for uk plus 1, uk plus 2 all the way up to uk plus m minus 1. Those m values if I find, then I know that uk plus m is the same as uk plus m minus 1 and so on till the end, okay, till the prediction horizon. And we also said that it does not really make sense to go beyond the prediction horizon, because a change that I make here will only affect an output after this, but our prediction horizon itself stops here. And if you assume the systems are causal, strictly causal, then up to k plus p minus 1 you could have kept making these choices, but we use this as a tuning parameter and then say, though I could make choices up to k plus p minus 1 to affect all the way up to k plus p of the output, I am going to stop at k plus m minus 1 just as a matter of convenience, and I am going to use this m itself as a tuning parameter in my MPC formulation. So, that is what we decide to do here. So, if you notice, then we think about putting all of this together as an optimization formulation. We see that we can define an objective function here, which says in all future time instance, whatever is the y, that has to be very close to y set point. So, I am going to say y k plus I minus y set point squared would allow me to have this y k plus I from I 1 to p be close to the y set point. And not only that, we also say at the same time I do not want to make too much control moves. So, I am going to kind of trade off both of these. So, this is the objective that I come up with. I could have simply come up with just this first term also, it does not matter. This is a more generalized formulation, and of course, we can make this even more general by adding terms for delta u and so on. So, that will not only say that I do not want to make very big control values, but at each instant I do not also want to make very big changes. So, if I want to have constraints that I want to impose on this, then I could either put them in constraints here, or I could add them in the objective function, and since I am minimizing this, all this delta u changes will also be minimized. Okay. So, there are two options, but traditionally people can put that in the objective function and then weight these various objective function terms and then correspondingly tune how aggressive I want my controller to be and so on. So, typically these two terms are definitely used. You could also use a third term delta u, and on top of it while you use it in the objective function, you can also put some constraints on u and delta u as a part of constraints also, it does not matter. Remember, the most important thing is once we have converted this into an optimization formulation, then you can pretty much do any of these things you want. You can add any number of constraints and so on, as long as you are able to pose problems that are solvable and meaningful. Now, when you look at this, so we talked about the objective function, we talked about constraints maybe on u, delta u and so on. And the third aspect of the objective function, the third aspect of the optimization formulation are the decision variables. And in this case, clearly I have to make a decision about uk, I have to make a decision about uk plus 1, k plus 2, k plus m minus 1. So, in a single variable case, I have these m decision variables that I have to choose. However, if you look at this formulation, it looks as if these do not participate here at all, other than here it does not participate here, but remember these terms or these decision variables participate here through the model. So, that is the key idea, because depending on how I change my manipulated variable values, the output is going to change. So, y k plus 1 will depend on uk, y k plus 2 will depend on uk and uk plus 1, y k plus 3 will depend on uk, uk plus 1, uk plus 2 and so on, right. So, that dependence on the moves that I am going to make in the future and the current move that I am going to make is captured by the model. So, if I put this model into this term here, then you will see the decision variables not only come in the second term, the decision variables also come in the first term. So, this whole objective function you can think of as some function of uk, uk plus 1 all the way up to uk plus m minus 1. So, The reason why I am writing it this way is I am showing to you that we have now got it into an optimization form, where it is a function of these m decision variables. I give it to an optimizer, and the optimizer will give me the values for these m decision variables. So, the model comes in this here, and that is where the model part of the model predictive control is relevant. The predictive part is here. So, how many outputs into the future that I am going to predict, and that is the predictive part here in model predictive control. And the control part is actually I am trying to find out what values I should keep for this uk plus 1 all the way up to uk plus m minus 1, right. So, these are the control inputs. So, once I identify these values, then I can actually control my system. That is where the control part of this model predictive control comes into picture. So, you see how this is different from your standard PID control, in the sense that there is a prediction horizon. It is not just immediate concern I have a concern about optimizing over a prediction horizon, and I am explicitly using a model for doing this control. I showed this before in one of the lectures, just to kind of bring that back here, so that we understand all of this comes together in model predictive control. Remember, I showed you that if you had a multiple variable optimization, there is this objective function, there are two decision variables. You can write this dou f dou x1 equal to 0, dou f dou x2 equal to 0, and get two equations to solve for this. Similarly, in the model predictive control formulation, based on what we saw in the last slide, I said the objective function can be written as some function of uk plus 1 all the way up to uk plus m minus 1. So, this function has both the model and the other terms and all that which we saw. Now, if I want to optimize this, then I have to do dou objective by dou uk is 0, dou objective by dou uk plus 1 is 0, and so on, and I will get dou objective by dou uk plus m minus 1 equals 0. So, I will get my m equations in these m variables, and then if I solve for this, I will get my m values, and then if you formulate it right, it will happen that the second order condition will be automatically satisfied. That basically means if I keep these values for these control variables, that would essentially optimize my objective function. It will actually minimize my objective function, which means that I am going to be able to follow the set point trajectory as closely as the system would allow me to do, while not expending very high control effort. So, I have the two terms, and I can based on the application emphasize one term, de-emphasize the other term, and so on. So, that is how all of this works together. So, in terms of an algorithm, what happens is you start and choose a control horizon m, you choose a prediction horizon p, and m has to be less than p, which we have talked about quite a bit. Let us assume that we are at time t equal to k. So, what we are looking for is we are looking for these variables to be optimized, and these output values to be very close to set point. So, which is reflected by this part of the objective function, and at the same time we want to ensure that the control moves are not very dramatic. Now, we said this objective function is a function of uk plus 1 all the way up to uk plus m minus 1. So, you optimize this is where you simply give it to a solver. So, we are talking about a formulation here, and the actual solution is really sent to an optimization solver, which will solve for this, and then it will give you the optimal control moves u star k up to u star k plus m minus 1. Notice that all of these control moves you are going to get at time t equal to k. So, at time t equal to k, you really need only one decision to be made, right, which is I have to implement a control move here. So, what you will do is you will implement this, okay, and then wait, and then you will go to t equal to k plus 1, and you will repeat this process and so on, and you will keep controlling your process. So, that is the way MPC algorithm works. Now, one question that you could ask is, if I am going to implement only one control move, why did I compute all of these control moves at time k? So, I will answer this question through two important points that I want to make. The first one is, forget why we compute all of this at t equal to k, but let us see what makes sense in terms of implementation, right. So, if I am sitting at time t equal to k and I have what is called this move plan, which is I have u star for k all the way up to u star k plus m minus 1. One option is to not look at this process till u t equal to k plus m, and then simply implement this move plan and keep implementing this move plan, and then once this move plan is exhausted, again do a batch of move plans and then keep doing that. So, that is one option. The disadvantage with that option is the following: when we make this decision for this move plan, we are sitting at time t equal to k. So, all the information that I have till now with me has been collected till time t equal to k, and I made my move plan, right. Now, at t equal to k plus 1, I have got more information, right, because I have got another output value y k plus 1, right, and at t equal to k plus 2, I got even more information, I have y k plus 2. Now, if I stick to my original move plan, then all this information that is coming in the future, I am simply going to ignore, I am not going to take advantage of this. So, it is something like this: supposing you are trying to study for an exam and you think that the exam is very hard, and you decide that you are going to put a lot of effort and you are going to solve some sample papers and then see how well you will do in your exam. Let us say you start studying today and you have planned for a week, and so after one day of studying you take a sample paper and do this, right. Now, if you find a sample paper very easy, right, you cannot stick to your original plan, right. You will calibrate based on whatever happened one day later your study pattern, right, because there are other exams that you want to do well. So, maybe you will reapportion time depending on where you are doing well, where you are not doing well, and so on. Similarly, if you did very poorly in the sample paper, then you know the effort that you have planned for this is not enough, so you will redo this. So, in that sense, it makes most sense to basically keep re-evaluating what is happening and not stick to your original ideas, and as and when there is new information that comes in real life, what we will do is we will recalibrate our plans and thinking based on that new information, right. If I say I am going to play for the next 1 week cricket and it starts raining, clearly you cannot do it. So, we have to re-evaluate plan, maybe I cannot play cricket, I have to do something else, and so on, right. So, that is an important idea for having a move plan, right, and only implementing the first move. Now, let us ask the flip question and say, if I have only one plan move that I am going to implement, why do I find all of these values is another question you could ask. So, here you can show this theoretically, but I am going to appeal to a little bit of intuition to explain this to you. This m you choose can be used as a tuning parameter to make the controller more or less aggressive, okay. So, if you have more moves in your bag, you can make the controller a little less aggressive than if you have a single move that you are making every time, or you think you are going to make every time. So, the idea is the following: supposing you are in a room, you are at one edge of the room, let us say you want to reach the other end of the room, and if I told you can jump 10 times and reach the other end of the room, what you will do is you will take measured jumps and go to the other end of the room. However, if I said, okay, you have only one move to jump to the other end of the room, what you are going to do is you are going to really try and jump very hard. So, you are going to be very aggressive about your jumping, right. So, that is the same thing that happens in controllers. So, if I say I have only one move that I am going to calculate, but there are several predictions in the future, I have to make them close to set point, then your controller is going to be quite aggressive. So, that aggressiveness in the controller could be traded off by choosing this m. A very long m will make your controller less aggressive, very short m will make your controller more aggressive, and so on. Now, one last thing, which is something that I wanted to talk about. The great thing about MPC is it does not matter whether it is a single variable problem or a multiple variable problem. It very easily extends to multivariate problems. So, here I am showing a case where if you have two outputs and two inputs, what will happen is we were only looking at this portion for single input. Now, when you have multiple inputs and multiple outputs, for each output you will also add on the effect of the other input, and you will also add the other outputs and the effect of this input here and this input here. Now, notice how this is structured, right. All of this simply adds on because we are assuming the underlying processes to be linear. So, it is a very simple extension to multivariate cases. Now, in the multivariate case, what will happen is everything else will remain the same, except now if I had single variable and a control horizon of m, I had m decision variables. If I have 2 inputs and if I have a prediction horizon of m, then I will have 2m decision variables to choose values for m values for u1 in from the current move till m k plus m minus 1, and m values to choose for u2 from the current k to k plus m minus 1. Okay. So, basically everything else remains the same, except that the number of decision variables that you are going to use increases by corresponding to the number of inputs that you are going to use. So, once that is done, then everything else is done in the same way. So, this is one of the major attractions of MPC, because when you go from CISO to MIMO control, you do not need much more sophistication. The basic ideas simply translate. So, in terms of a summary, the unique features of MPC that help us are use of an explicit model, use of a moving horizon, and explicit optimization to calculate control moves. This is something we have talked quite a bit about. The advantages are easy to incorporate constraints, I talked to you about. Extension to multivariable case is straightforward, which I showed you in the last slide, and extension to nonlinear problems is also straightforward, because remember at the beginning of this lecture I said we can make the formulation however complicated we want, right. We can take a model which is nonlinear. So, from a formulation viewpoint, nothing is going to change, except that instead of a linear model I am going to say there is a nonlinear model. So, we kind of move all the burden of solving to solvers, and you have lots of people working on solving different types of optimization problems, complicated optimization problems, convex, non-convex problems and so on. So, you can basically take advantage of all the advancements that are taking place in the optimization area, and then use that in solving MPC problems. So, in that sense I do not have to generate new theory if I want to solve nonlinear problems, whereas traditional approaches, whenever you go to a nonlinear problem, you are forced to develop a new theory, and the new theory will depend on the type of nonlinearity you are looking at and so on, and there will be lots of restrictions in terms of what kind of nonlinearities can be addressed, how do you address them. So, you will require different tools for different types of nonlinear problems and so on. So, we kind of get rid of all of this. When I say get rid of, we kind of push everything to the optimizer, and from a formulation viewpoint we have a clean idea of what we are trying to do. So, with that, this portion on model predictive controller is complete, and you will also have a tutorial on how to implement MPC controller on a simple example. Thank you.